Okay, the next thing that chemistry people always use, instead of using F's and G's, what they actually use are delta F's and delta G's. Woohoo! So now we're going to come to section 10.4. Delta F and delta G. What is delta F and what is delta G? So changes in Helmholtz free energy. So number one, changes in Helmholtz, I can't spell, Helm, Holtz free energy, delta F. May I write the equation as delta U minus T delta S minus S delta T? My F was U minus TS. So then may I write the changes as that? Okay. Now, is temperature constant for this case? Implies delta T is? Thank you. So may I write this as delta U minus T delta S? Is delta U from the first law? What is delta U? Thank you. So may I write delta F as Q plus W minus T delta S? Where Q is what? Heat added. And W is what? Useful work. Done. Now, there are two situations that we worry about. One is when entropy, no new entropy is created. And when new entropy is created. So when there is no new entropy created, that means delta S is 0. And that is only possible when Q equals 0. Because what is delta S? Q over T. So that means my above equation reduces down to just that. And when delta S is created, that means T delta S is greater than 0, which means delta F must be less than the work done. So we can combine these two expressions together to give me delta F will always be either less than or equal to the work done. Number 2. Changes in Gibbs free energy, delta G. What was the definition of Gibbs free energy? H minus TS? Is that how we defined it? And what was H? then may I write delta G as delta U plus P delta V plus V delta P minus T delta S minus S delta T. Everybody with me so far? Everybody understands how we got there, right? Bobbleheads? Yes. Okay, so now what do we know about Gibbs free energy? Is T constant? Which implies what? Delta T must be 0. Is P constant in these processes? Which implies delta P must be 0. So then may I rewrite this as delta U plus P dV minus T delta S. And then may I rewrite this from the first law as delta G equals Q plus W plus P delta V minus T delta S. Now, again, there are two cases. Case 1 is when Q minus delta TS is 0, which implies delta G. Do you guys see how that Q minus TDS came into existence? Okay, this is, oh, by the way, what do we know about entropy? So can I write this as that? And then can I write this as that? Mathematically, am I allowed to do that? Okay. Can I erase this part? No? Oh my God. This is, oh, by the way.
Yes, and oh, by the way, is an important note.
Because a lot of times we forget stuff.
Okay.
The students online are thanking you for including an oh, by the way, and leaving.
Oh, okay. Well, the students online will see
And they
this.
appreciate your humanity.
Of making
They
sure.
demonstrate in
Oh my
class the
goodness.
concern for
Let
society.
them see this. It's good that it's there. It's just the case. It's like,
You don't have to scroll between pages or between episodes in
Yeah.
order to see where it came from. It came from here now.
Oh, okay. So this means my equation, what do we call this equation? A what? A crying face? No, a smiley face.
crying face. Water bottle.
Can't be a crying face equation.
It should be.
Equals work. All kinds of work. And when this term is not 0, but it's rather negative, delta G is less than work other. Therefore, we can combine again these two equations to give us a condition that delta G must always be less than the work done. Okay, so how does this all help us when we're looking for chemical reactions? Okay, so moving on, so summarizing. Wait, I have already that in there.
Delta G equals delta H minus T.
Yes. So in other words, I should be able to write this as a very small method as delta H minus T delta S. That's what you need to remember. Now, how does this help us when we're talking about chemical reactions? So guys, in chemistry, this is going to seem familiar to you guys. Okay, I can do that.